So, chi-square test of independence, what we did was we test to see if there was an association between two categorical variables. One of them could have been a number, the other one probably wasn't a number. The other variable was maybe a yes or no type answer, or a political party, or a favorite class, something like that. But in a lot of cases, you want to test to see if there's an association between two numerical variables. In fact, back in chapters 7 through 10, we talked about linear regression. Okay, linear regression, and that's what we're going to review right now. We're just going to review. We're not doing a test right now, but we're going to review linear regression. We did problems like this, exactly like this in our examples. We had it on our test in chapters 7 through 10. So our scenario is, here's our problem. When people have colds, common wisdom says to avoid dairy products since they produce extra mucus. Did any of you ever hear that? Like if you're stuffed up, don't drink milk? No. Okay, some of you have never heard it, some of you have. I always heard it, my mom and dad always said, well, don't drink milk when you're all stuffed up because it'll make you more snotty. Okay? So, or dairy products. So, you feel like what? Oh. Well, maybe we could do an updated test for this. So, anyways, they tested this claim in 1990 in Australia, and here's what they did. They actually infected volunteers. So these people volunteered. They said, I volunteer to be infected with a cold virus, not like a zombie killing.
Is that ethical?
It is. They were, because they were, listen to that. They were volunteers. So they knew up front what they were getting into. It's like volunteering for a research, like if you have cancer or some disease that you're going to volunteer yourself to be part of an experimental study. So it's ethical because they know up front what they're getting into. This may or may not work. You know here that you're going to get a cold. And it's not deadly. So they infected them with the cold virus, and then they assigned them at random to drink different amounts of milk. So some of them had, as you can see from the data, 0 glasses of milk, 1 glass of milk, 2, 3, and 4 glasses of milk. And then they all used tissues, and here's the disgusting part. And so they all blew their nose, and they took all of their tissues and they weighed and measured the nasal mucus secretion. So they weighed their snot.
At least you're being accurate with it.
What?
At least you're being accurate.
Well, yes, exactly. So that's what they did, and these were the amounts of mucus produced by the people that drank these glasses of milk. So you can see that we have two numerical variables. So what are we going to have to do with these variables to get a linear regression line? We're going to have to put them in lists. So you're going to have to go to stat, turn it on first, stat edit, and you're going to have to put them into two lists. Yep, there are 3. So the first list, there's basically 3 zeros, 3 ones, 3 2s, and so on. Okay, so you entered the data in a list, and we're going to come back to that on the next page. We want to answer some questions, though. These are, again, typical questions asked about a linear regression. We've got glasses of milk and ounces of mucus. So we want to know how many factors were in this experiment.
1.
1 factor. Okay, what was that 1 factor? Amount of milk. Very good. So 1 factor was the amount of milk. How many levels were there for the amount of milk? 5 levels. They were 0, 1, 2, 3, and 4 glasses of milk. So the levels are the different numbers or amounts of milk that those people were getting.
What if they were different type glasses?
They're not.
No, they didn't say that.
They are,
Sorry, but
no, they are, okay, glasses of milk. So what are the treatments? Well, we actually already listed them. The treatments are 0, 1, 2, 3, and 4 glasses of milk. Those are the treatments.
Is a factor
Factor is what you're manipulating. So factor is what you're manipulating. So you are manipulating the glasses of milk.
And then the levels are the number of manipulations.
Yep, number of manipulations. Very good. And so the treatments are just each of those individual levels listed out. So what are the experimental units? What are you doing, what are you giving the factors to, or the treatments to? Volunteers.
In Austria. I mean Australia.
Okay, volunteers. And we could call them infected volunteers. Volunteers who have a cold virus that you've given a cold virus to, but volunteers. Now, how is randomization used? In other words, how do they make this an experiment? How do they randomly assign something?
Randomly assign the amount of milk to each person.
Very good. They randomly assign the amount of milk each person will drink. Okay, what is the purpose of randomization?
And then
To account
somebody
for
gets more
natural
sick.
variables.
Okay, I heard Hannah. Hannah said account for natural variables. What did you say?
So like if somebody got more sick than another person, it would make it take away the possibility. I don't know, like I mean.
Like reduce variability is kind of what you're saying. The light. Yeah, basic. You're both saying the same thing. That's right. In case someone got more sick than someone else, you know, they were more affected by the cold virus.
Or someone naturally produces more mucus.
Yes. Yep. Someone naturally produces more mucus. So its purpose is basically to reduce variability. Or eliminate confounding variables. Very good. Eliminate confounding variables. And randomization, its purpose is also to establish a cause and effect relationship. So the randomization here in the experiment is necessary to establish a cause-effect relationship. A cause and effect. So in other words, drinking more milk causes more mucus. That's what we're hoping to say. That's what we're hoping to say. So how is replication used?
Like they have multiple people.
Yes, very good. Multiple people get each treatment. Exactly how many people get each treatment? 3 people get each treatment. So 3 different people drink no milk. 3 different people in the experiment drink 3 glasses of milk. So that's replication. More than one of the subjects having a treatment. And what is its purpose?
So you can compare. Well, no, not necessarily.
Also to reduce variability. Yes. All right, now we are going to be doing our sketching of our scatter plot and least squares regression line. So now that we have our data entered in our list 1 and list 2, we can go to, basically we can go to our stat plot first. And we want to turn our stat plot on, and the type we want is the first type of graph, the one that just has the scattered dots, a scatter plot. Mine's highlighted, but it's flashing, so I'm actually not going to get that until I hit enter. Now it tells me where's my X list in. Mine happens to be in list 2, and my Y list is in list 3. And then whatever kind of dot you want. And then you want to hit, you could almost hit zoom 9. If you just hit zoom 9, it'll graph that for you. So there's my scatter plot, which I need to basically sketch a graph of. What should my x-axis be labeled? Glasses of milk. And my y-axis, amount of mucus. Without labeling your graph, you don't really have a graph. You can't just put dots here. You can just put dots on a normal probability plot, or what would a residual plot? You don't need to put labels as far as what they are, just X and Y. But on a regression, you've got to put the dots. So glasses of milk would be 0, 1, 2, 3, and 4. So if you notice, each of these 0, 1, 2, 3, and 4, they each have 3 dots above it, right? Yes?
For the amounts of mucus, do we need to specify that it's in ounces? Or?
That would be great if we specify that, yes, it's in ounces. So if I just look at my values, I've got like 1 would be right here, and that would be 0.5. And so if I'm going to make that 1 and that 0.5, that gives me just kind of a, and I can always hit trace here, and it'll give me my values. So, you know, you're just kind of guesstimating where these go, just doing the best you can. Just get a general picture of what this looks like. So there it is. There's my scatter plot. So now we need to write the least squares regression line and draw it on here. So the way we do that is we're going to go to Stat, Calc. So Stat, Calc, and we would like to do linear regression A plus BX. So number 8, you're going to do linear regression A plus BX, where A is the y-intercept and B is the slope. The number in front of X is always the slope. So I'm going to do that type of linear regression. My X list, you tell it where your X list is and your Y list. You don't have anything in your frequency list. If you want to store the regression equation, it's pretty easy to store it. Just follow my steps right now. To store the regression equation, you're going to hit VARS, hit VARS, go over to YVARS, hit enter, and enter again. And you just put Y1 is where you're storing your regression equation. And then hit calculate, and it gives me my linear regression equation, which is y equals A, which is 0.64 plus 0.057x. It also gives me that r squared is 0.0568 and r is 0.2382. So that's all the information I have. If I want to write this equation more appropriately, what I would write, the y is the amount of mucus, so I would write amount of mucus equals 0.64 plus 0.057 and then times glasses of milk. Or you could just say amount of milk. So that times that. And that way, instead of if you use the words instead of the X and Y, it makes it easier to explain things, knowing where to plug things in, and it shows that you have a better understanding. All right, so now we need to, this is our least squares regression line. We need to actually put it on here. So all I have to do, since I stored it, if you stored it like I did, hit graph. Oh, I better go to y equals. Oh, I'm not in the right mode.
When you did the R's,
They were in the, ask me afterwards if your calculator didn't give them to you. I can fix it. But not right now.
what did we do for the frequency?
There's nothing in the frequency
Okay.
list. So now, since you put it in here, the R was given to me when I did the linear regression test. Okay, so we can fix that later. All right, so there's it. By storing it, I stored it there. So now when I hit graph, it shows up, and it's kind of right here. So this is everything they ask for. If you did store it right, it would have popped up. If you didn't store it right, just go to Y1 and type this equation in. It's best if you can store it because it's amazing how much a little rounding changes the graph. So if you can store it, that's best. So